In this example, we want to determine if there's a unique solution that satisfied this linear system of equations. Now here we're given already the A, the X, and the B matrices, or A matrix, X, and B vectors, but they would come from the equations that would be 3x plus y plus z equals 10, negative x plus 3y plus 2z equals 5, and 6x plus 2y plus 2z equals negative 1. So we can go through and try to find if there's a solution. So let me first put in these A matrix, because we'll have to do that no matter what. And I'll put in the B vector as well, is 10, 5, negative 1. Now just looking at it here, this one by inspection is easy enough to determine that we do not have three linearly independent equations. If we look at the top row of A and the third row of A, we see that actually it's very easy to see that the third row is just the first row times 2. So we can multiply, it's a linear combination of the other two. If we do row 1 times 2 plus 0 times the second row, we get the third row, meaning that these are not linearly independent. Now, if the third entry was 6, 2, and maybe 3, in that case, there's no combination of the first two rows that could get us the third row. And in that case, we probably would have a unique solution. And we can test that out in a minute here. But let's look at what we were presented, and we can kind of prove mathematically that these are not going to be linearly independent from what we've just observed. Right, we have the A matrix and the B matrix. So the first rule is the size of A matrix square, or is A a square matrix? It does satisfy that. It is square. But what we want to look at is what's the determinant of A to see if it's a singular matrix. And we see that A has a determinant of 0, meaning we cannot take its inverse. And if we try taking its inverse, we see it gives us all infinites. It's all undefined. Since it's not invertible, since it is a singular matrix, we do not have a linearly independent set of equations. We don't have three linearly independent equations to match our three variables. Therefore, we cannot expect to have a unique solution to this. And if we look at the condition number of A, we're going to get something very large compared to what we've seen before, 1 times 10 to the 17th. So by looking at the determinant of A, it is singular. We don't have as many linearly independent equations as we have variables. And we see that if we do try to find x using that forward slash, that we don't get real answers for this. We get not a number, negative infinity, and infinity. We don't get that unique set of equations that we were looking for. But let's say we change A slightly. Say I just change that to a 3 and kind of reassess what we have. So this would be a different set of equations, and we want to test if this set is linearly independent. Again, it's still square, so it's 3 by 3. Now for this, just changing that one number here, the determinant is 10. It's not 0. The condition number will be finite, only 22. So this tells us that we should expect to have a unique set of solutions since it is not a singular matrix. It is invertible. And indeed, if we run this whole thing and we solve this, we do get a unique set of solutions for x in this case. But again, as a reminder, that was not our original matrix. That was our original, and we find that it is not three linearly independent equations for our three variables x, y, and z.